Okay, so it's time we started up the next talk. I'm very happy to have Tomohiko here from MidoNet to talk about MidoNet.
Hello, I'm Tomohiko. Okay, today I'm going to talk about basic OpenStack Neutron MidoNet talk. Yeah, it's. So before start, let me ask you, how many of you develop or maintain OpenStack? How about Neutron? Okay, only a couple guys. Okay. Damn. Okay. Well, it's a little bit about me. So I joined MidoNet 2 years ago. So now working on like a network state database team, developing communication channel between Neutron plugin and to the MidoNet agent. So before that, I worked at Google for 5 years, but I was on a web search team, so I did quite a career change. I used to write Python to generate data for search ranking. Then now I write Python for the plugins. Anyway, in my spare time, I do salsa, so I hope to catch some salsa tomorrow, but anyway, sorry, bit of digression. So first I can do a quick review on what networking challenges that we face now. Then talk about how OpenStack and Neutron solves that and approaches that. Then finally I explain how Neutron combined with MidoNet can better approach the problem. So I don't know. It's okay. So we live in the 21st century, so more devices than ever are connecting to the network. Every kid has tablets, maybe 2 or more, 3 internet-enabled hardwares. And with Internet of Things and IPv6, number of IP addresses are soaring. As a result, so more increasingly complex routing configurations. Most of the houses will have some smart grids, and also kids are downloading YouTube on this. But I guess we want to have a separate routing for smart grid than the internet, than the network that kids use for internet and stuff. And more security, of course. We need better and more finer grain and more flexible security. So what SDN, network virtualization, what we want is, first of all, it's got to be simple. Simple, easy to use, easy to operate, easy to maintain, SDN or virtualization. Then it's got to be scalable. It's good that SDN is fast, but it's got to be scalable and flexible. Dynamically, elastically, need to cope with traffics, and it's got to be fault-tolerant. So of course, network is bound to break. So even if a couple nodes may go down, but we still need the networks need to function as normal. Then SDN network virtualization is gotta be API driven. So we gotta be able to programmatically define and control the behavior of network. So it should provide clearly defined API, and we don't want to go to each router and servers to do manual configurations. And of course, it's good that we have it's good that SDN or network virtualization, it does smart stuff. But if it's if it adds too much overhead and it's slow, nobody's going to use it. I guess that's why most of the data centers and carriers are still using, not so eager to move on to SDN. So I guess that's enough for the introduction. So first, let's look at how OpenStack or Neutron, solve the problem. So I guess most of you know that OpenStack is a infrastructure as a service project, and Neutron is one of the those sub-tracks, or I don't know. So it provides networking services. More specifically, Neutron provides northbound API, and so it consists of northbound API and bunch of software-defined networking vendor plugins, including MidoNet. So let's look at the reference implementation that Neutron provides. It consists of Neutron together with Open vSwitch, as known as OVS. So I guess there are 5 basic elements that no matter what it is, all the networking service needs to provide. Basically like L2 connectivity and L3 connectivity together with routing and SNAT gateway stuff and floating IP or whatever, or it's NAT, then security groups or security controls. So because Neutron, the reference implementation uses OVS. So OVS, naturally provides the L2 connectivity. So, we compute whatever necessary, and compute data paths and flows, and we install it in OVS in a kernel, and so it does the basic L2 connectivity stuff. For the L3 connectivity, so we use they use namespace together with Linux bridge. And why we need Linux bridge? Because our Neutron security rules are based on IP addresses. So, but OVS doesn't natively integrate with IP tables, so that's why we need namespace together with Linux bridge. And also so that's the left-hand side. The right-hand side, the network node. So, so all the rest of the routing, like security controls and SNAT gateway stuff, is taken care of by those network nodes. So what's good? The advantages of reference implementations is that first of all, it's all open source. OVS, Linux bridge, namespaces. Those are commonly available. Everyday tools that all the Linux developers use. So everybody loves Linux. So it's good. But at the same time, so the challenge is that this basic reference implementation policy is that first of all, all the traffic needs to go through that central network node. So so it uses a centralized control model. So and all the L3 routing is done at the network node. So and that central network node naturally becomes a traffic bottleneck. So as a result, it's susceptible to traffic, trombone, meaning that the same different VMs. So when 2 VMs communicate to each other, even if they are hanging down the same bridge, the packets will still need to go up to the central network node. So just to get sent back to the same bridge and to the target VM. So that means single point of failure. So this central network node becomes a single point of failure. And of course, Neutron provides HA solution, but for that we need virtual routing redundancy protocol. So we think that the basic implementation is already complex and a bit hacky, and adding VRRP on top of that is kind of just adding complexity. And of course, Neutron provides solution to this, which is distributed virtual router proposal. So, so now with this model that routing is pushed down to the compute node, but again, there's still a problem because SNAT is not implemented with DVR yet. I'm sure it's going to be implemented, but people are still discussing how to do that correctly. And because of that, it still requires central network nodes. So I don't know. Overall, people at MidoCloud think that it's still a bit hacky and kind of hard to scale. So having said this, so let's take a look how MidoNet together with OpenStack approaches the problem. So MidoNet is so one of the open source Neutron plugin, and this is important. We open sourced MidoNet and its source code in last year in November 2014, and it's important. So I repeat, so we open sourced it. So that thank you, because still not nobody, but many people don't know that. So MidoNet is network virtualization overlay solution. So I don't know, it's hard to see, but so what do we mean by network overlay? So below is a physical network. So there's a intranet private IP network connected to a bunch of hosts and VMs on top of it. So these are naturally the gateway nodes and connected to the internet with multiple uplinks. So these are physical world. Then on top of that, it builds a virtual network as an abstract layer of logical topology or logical networks. So basically, so those uplink ports are mapped to virtual port to this abstract provider virtual router, and below that, so we sort of logically create a tenant router under which we can have multiple more routers. Hanging down, each of those may correspond to some department or whatever logical unit. Then to those virtual router, so we assign a network and virtual port, and those ports are mapped onto VMs hosted on some machines. Anyways, so basically, in the physical world, it might be just a simple leaf and spine, typical data center layout, and we don't really care. And on top of that, MidoNet allows to build virtual layout. So basically, just simply internet and some provider network and some logical tenant routers and networks. So there's a clear separation between. So it allows clear separation between physical and logical worlds. So what's important here is that we separate virtual world from physical world. Well, this picture kind of scares me because now people are go Wi-Fi, but still machines, of course, in the data centers are connected by cables, and so ideally, because of this separation of physical world from the virtual world, virtual network changes don't require, of course, the changes in cable connection between physical network, and because of that, physical networks also can get simpler. The leaf and spine LTE plus ECMP is a good design, and corollary to that is, so we can use cheap white box hardwares for routers and stuff. It doesn't have to be OpenFlow enabled, or you can use commodity servers. And the corollary to that is virtual network also can become flexible and a bit more easier. So another feature of the MidoNet is that it's highly distributed. So we don't require no central controllers. So we do processing at the edge. So everything is, because if we don't do processing at the edge, so that means that the packets, we need to send packets midways to like some service nodes such as or middlewares to provide service such as floating IP or security operations or NAT and stuff. By the way, it's a picture of Vandercliff. It's supposed to be somewhere in Australia. It looks like a end of the world. So anyway, I wish I could go there sometime. But anyway, so because we do processing at the edge, there's no, and because we don't require any central controller, no single point of failure, and because of that, so it's more fault tolerant. And I guess I quickly go over how we handle packets in a distributed manner. So, so there is a state information for network, and two types of network state. One is more static information is like virtual topology information. How many routers, how many bridges, how they are connected, and on which bridge, which VM is connected, and which port corresponds to that kind of stuff. And also dynamic state information, app table entries, MAC IP mapping, and so routes, like including BGP routes, and those static dynamic information. Those are stored in network state database. Right now we use Zookeeper, and because of that, this network state database is not a single point of failure. It can also can be distributed and fault tolerant by adding more Zookeeper instances. And those information is asynchronously and on demand sent to our agent that lives on each host machines. And for that communication, we recently began using reactive framework. So these are passed as a kind of observable of, say, bridge or observable ports and stuff. Agent receives those information asynchronously and builds back up the model or bridge and stuff. So then all the simulation is done locally. So we don't make any blocking calls to the central network state database node. So all the simulation is done locally, and because all the state information, such as bridges and also app tables, are cached locally, and because of that, we don't have packets don't need to go through the central traffic network node and no traffic trombone, and of course all the information is there. Computation is fast, and so don't know how much time I have, but
you've got another 10 minutes if you want.
okay. So quickly I go through. So central. Sorry. So network state database sends state information that's propagated to the agent that live on the edge on a host machine. So so when VM sends first packets, if in lookup the Linux kernel, and if the database path is there, there's no need to do anything. But if it doesn't, then there's a netlink upcall to the MidoNet. So then agent locally processes packets and do some simulations, install local flows to the Datapath. And just for the, I think I forgot to mention, but so after the simulation is done, we create the tunnel between the source and target, and so packets are tunneled through to the peer host, to that tunnel, and decrypt So, anyway. So a MidoNet agent on the target host maps tunnel key to the kernel Datapath port and installs forward flow. Then the subsequent packets don't need any simulation. It just sent via tunnels and no overhead. MidoNet adds a small amount of overhead for the first packet, but that's it. Still, SNAT and security group require some connection tracking because the return packets may not come through the same gateways. But those state information we used to use Cassandra, but that's a blocking code. Then that adds some overhead. So we ditched that model, and now agent passes those state information for SNAT and security group by RPC between so it's a peer-to-peer communication basically. So because of this, there's no blocking codes to like Zookeeper or Cassandra or whatever. So everything is done locally. So I guess I gotta wrap up. So summary, I guess because of this, using the overlay approach allows us to separate physical world from virtual world. So I guess that simplifies a lot. And I guess virtual net overlays, I think, is easier to debug and also maintain. Then it's scalable because no single point of failures. You scale out. We can easily scale out by adding more servers and hardwares and stuff. Then it's fault tolerant. So if one agent goes down, yeah, that machine will go down, but then the network will not go down. So there's no single point of failures, and the rest of even if a node goes down, the rest of the network still function normally. And fast packet processing, we came a long way about this. So I guess MidoNet agent used to add a lot of overhead, but then we ditched. We cached all the data locally, and we ditched Cassandra and doing RPCs. And so now the overhead the MidoNet agent adds for processing packets is very small. So it allows, and unlike central control node model, we don't need any we don't require any communication with the central node. So it's pretty fast about packet processing. So I guess that's it. So thank you. Any questions? Yes.
To get sort of east-west traffic, do you need to use Open vSwitch for that, or can it be encapsulated by sort of VXLAN or something else?
So we also have integrated with a VTEP. So yeah, we can the VXLAN and the GRE tunnels can be used.
Right. Okay.
So you mentioned you used Zookeeper, right? Like, what's the purpose of Zookeeper there?
No, that's okay. The question is why and for what we use Zookeeper. I guess Zookeeper is usually used for consensus, but we use it for, well, first of all, storing virtual topology information, and also the up table entries and stuff. And why we wanted to use Zookeeper? Because it provides a watcher mechanism. So suppose virtual topology layout is stored in the Zookeeper. Suppose port is added to the bridge, then that so agent first subscribe for the information for bridge. For that, so we install watcher. So Zookeeper provides a watcher mechanism. Then whenever there's an update to the topology, then Zookeeper notifies via watcher mechanism to subscribing agents. So those updates are sent over Rx Java as a observable. So and those are sent asynchronously and builds back up into the agent side view of bridge and so on. So does that answer the question?
To some extent. Similarly, do you have integration with Apache Cloud Stack?
Apache, sorry?
Apache Cloud Stack.
We used to, but not now, I think.
Thank you.
Are there any other questions? Sounds like no. Thank you very much.
Thank you.